These will be the first notes on acids and bases. Many chemicals fall into the category of being an acid or being a base. A third category we will address in the notes are about salts, which is another very common category for many chemicals to fall in. We are going to understand the nature of each category and some of the definitions and the way they behave. To understand acids, what you really need to understand, first of all, is what a hydrogen ion really is. When you think about a hydrogen atom, it's really easy to think about hydrogen atoms. You should spend a lot of time thinking about hydrogen atoms because it's the only atom that we fully understand in chemistry. Honestly, every other atom has something about it that we have a pretty good model but haven't perfected it. But hydrogen is just so simple and easy. We can fully understand it, and that's great because it's the most abundant element. Well, a hydrogen atom is really just a proton and an electron going around it. That's very simple. Sometimes it has a neutron, but that would be deuterium. Sometimes it has two neutrons, that would be tritium. Those are less common. Those are just isotopes, and we're going to ignore those for the time being. If there's a neutron or if there's two neutrons, it really has very little effect on any of the things we're talking about other than the mass. And because those isotopes of hydrogen are so rare, we're going to pretty much just pretend they don't exist for the purposes of understanding acids and bases. So that's a hydrogen atom. It's a proton in the middle, as you should know, with an electron buzzing around it, that 1s1 electron in the first energy level. And what is a hydrogen ion? Well, a hydrogen ion is when it loses that electron. What's left? Just the proton. So a hydrogen ion is really just a proton. Whenever you have a lone proton floating around in the universe, that is considered to be hydrogen, because that's what makes it hydrogen, having one proton. If it's an atom, it has that electron, but it doesn't need that electron to be considered hydrogen. If it loses the electron, it's still hydrogen, but now it is an ion. It's very important that you understand this. And a hydrogen ion is very different than any other ion that exists because it is so much smaller. It's many orders of magnitude smaller than the next smallest ion. So hydrogen ions have many unique properties, and that's really why we have these categories, acids and bases. If you really want to know why we call things acids, it's because of the hydrogen ion. Hydrogen ions are protons, and protons will stick to things, as we shall see. A very important vocabulary word in this section to understand acids and bases is the word dissociation. You might think the word should be dissociation. A lot of people will say that, but the word is actually dissociation. When you associate, you hang out with something, you hang out with your friends, and when you dissociate, well, you say bye-bye to your friend. It's saying bye-bye. We've seen this word before when we talked about ions, ionic compounds dissolving in solution. This word did come up if you noticed, and you might have been led to believe that the only things that dissociate are ionic compounds. Well, that's not entirely true. Another group of chemicals that dissociates are the acids and many of the bases. So this word is very critical for this unit. I haven't emphasized it a lot yet. You might have already picked this up, but just to be sure you realize what the word means. Dissociation is splitting up, breaking apart, ionizing, saying bye-bye, all of those things. So here's an example. HCl is a molecule. It's not an ionic compound, but it will often dissociate. That means the hydrogen breaks off and the chlorine breaks off, becoming chloride, and you wind up with two ions, positive and negative. This is critical for understanding acids as well as bases. So dissociation, know what that word means. Understanding acids and bases involves a very good understanding of the water molecule. H2O, the most famous chemical formula in the world, is the formula for water. You should know a lot of things about water by now. You should understand why it has that shape as a molecule, kind of a tetrahedron, really. And you should know whether water is polar or nonpolar. Remember that? That was kind of important in our last unit. That's kind of important in everything in chemistry, really. So what is it? Is water polar or nonpolar? Water is a polar molecule. Not just a little bit polar, water is extremely polar. I like to think of those two hydrogen, if you flip that water molecule over, as the muscles. There's a bunch of analogies, like the Mickey Mouse head, or those could be the muscle arms of the water molecule. It's a really tough molecule. Well, remember, polar molecules have a positive and negative side, the delta positive and the delta negative side. So if something that has a charge goes by them, well, they like to grab it and stick to it. That's the reason that we saw things mixing with water. That's the reason we saw solubility, okay, of ionic compounds, for example. So what would happen if a hydrogen ion went drifting by the water? Well, hydrogen ion has a charge, doesn't it? What kind of charge did it have? Oh, wait a second. A hydrogen ion is really just a proton? What's the charge of a proton? +1. So a positive charge is going to stick to a water molecule. If that proton comes along, it's going to stick. Now, which side of the water molecule is the delta negative side? Well, which one of those has a higher electronegativity, the oxygen or the hydrogen? Definitely the oxygen. Remember, oxygen is the silver medal winner for electronegativity. So if a hydrogen ion goes drifting along, it's going to stick to the oxygen side. Well, now we don't have H2O anymore. We've got H3O, and it's got a positive charge, H3O positive. Now, I know that looks weird. It kind of disturbs a lot of people to see that. They think it's some kind of joke. But no, it's not a joke. This is actually a very important ion. I would argue it is the most important ion in all of chemistry. And you may not have heard it before, the name of it before. The name of this ion is hydronium. So the hydronium ion, H3O positive, is really what does all the things that we give credit to acids for. They do the work of an acid. Very important ion. So what we're going to see is this is the real deep down acid. Every other acid just makes this. And once this is made, it has a lot of reactions. It has a lot of results, let's say. So hydronium is critical for understanding what acids are really doing and their properties. Hydronium, H3O positive. When we're learning about acids, it's important to know a few things about them. Okay, what they look like, even what they taste like. Now remember, in a chemistry lab, we never ever taste the chemicals. They used to do that in the bad old days, and many chemists had poor consequences, poor outcomes, let's just say. Okay, tasting chemicals in a lab environment is forbidden. It's against lab safety rules. However, you actually encounter acids all the time in your everyday life, and you already have tasted them. So it's important to recognize the acids that you already have tasted and what that taste is, okay, and what they look like. Well, the best one to start with is vinegar. Vinegar is the OG acid, the originator, the very first acid that was recognized in the ancient world. Okay, well, vinegar is used for many things. It's used for cleaning in its distilled form, concentrated form, and it's even used in an oil and vinegar salad dressing, a lot of salad dressings, and many other foods that we eat. So vinegar has kind of a sharp taste, kind of a sour taste, okay? Another thing that we consume that contains acid is fruit juice. Every fruit juice contains acid. Usually it's citric acid in many cases. And the best example to picture in your mind is lemon juice. Okay, lemon juice is very, very sour. Okay, also colas, sodas, most soft drinks contain acid. In fact, to be carbonated, you actually have to contain acid because carbonic acid is what makes soda bubbly. So we consume acids all the time. Even Pellegrino or Perrier is an acid, okay? So we consume these all the time, and what characterizes all of those? Well, they're not all the same, but they all have a tart, sour, or sharp taste. One way to describe it is it feels like it's maybe biting your tongue, okay? Like in the case of sparkling water, it feels like it's got a little bite to it, okay? Or it might taste sour, like think of a lemon or a lime. So that's really where the word acid comes from. It comes from the Latin word for sour. The substances contained in all of these things can be described as acids. Then there's many other acids, such as sulfuric acid and hydrochloric acid, which we would never really want to taste because it would kind of burn away our tongue and we wouldn't be able to taste other things later on in the rest of our lives. So that's the reason we never taste anything. Well, for one reason, the glassware in a chem lab is never sanitized like it would be in a kitchen. It's just cleaned up enough that we can use it again. And of course, some chemicals can actually cause major harm. So that's the reason that we never consume them in a lab. But you are supposed to realize that they have that sour taste. If you had to pick one, I would say sour. Think of lemon juice. Even though hydrochloric acid is often represented by the formula HCl, and in parentheses that's an AQ, that's aqueous. Remember that means it's in a water-based solution. Water is the solvent. Hydrochloric acid actually consists of dissolved hydronium, H3O positive, in solution, aqueous, and chloride aqueous ions. Why is that? Because when you put the HCl in water, look at this formula, HCl, hydrochloric acid, plus H2O, water, what actually happens is, what's that D word? Dissociation. It dissociates, and what you wind up with is hydronium and chloride. Okay, well, the chloride ions, they don't really do much. Chloride ions will just sort of float around in solution, maybe for billions of years. In fact, in the ocean of the Earth, we've got probably some chloride ions that have been floating around there for probably billions of years. And once they become an ion, well, they're less reactive. They just sort of float there until maybe the water evaporates and then they form some salt somewhere. But those we don't usually worry about. That's not going to be the big deal here. The big deal is the hydronium ions that are formed, the H3O positive. Those will do lots of things. Those will have reactions with bases. They'll have reactions with metals. They will change the conditions of the solution, what we call the pH. Lots of things will occur because of that hydronium. However, this step is often left out of many chemical equations. A lot of times they don't point out that hydronium forms. They skip over this and go to the final products of the reaction. If you imagine the hydrochloric acid in aqueous solution, well, it would look something like this. The water would not be this organized. This is just so it's very, very clear what's happening here. The HCl is a polar molecule, but it's not strong enough to stand up against the pull created by the water molecules. The water molecules try to grab hold of the two ends, and what they wind up doing is ripping it apart. That's the reason it dissociates. Molecules don't just suddenly dissociate for no reason. They have to kind of be ripped apart. So dissociation is the polite way of saying that they get ripped apart. So watch what happens when they get ripped apart. The HCl becomes the chloride ions, well, don't worry about them too much, and the hydrogen ion, which sticks immediately to the nearest water molecule. It doesn't make it very far. It is grabbed immediately by the very first water molecule. And so now you've got hydronium. That is what we call the dissociation of an acid. Every acid does this. Every acid generates hydronium. So obviously, if it generates ions, if every acid generates hydronium, and hydronium is an ion, well then acids are electrolytes. So that means their solutions in water are conductors of electrical current. Like other electrolytes, hydrogen chloride dissociates to produce ions. The thing about hydronium though, here, what's the formula for hydronium again? H3O positive. There's your hydronium. Hydronium isn't just like any old ion. It's not just any old electrolyte. It is the best electrolyte. Now, why is it such a good electrolyte? Because remember, the thing that makes it hydronium is that it has that little proton stuck onto the end of the oxygen. But that little proton can easily hop along to the next water molecule or the next, and it can travel through the body of water. Because it is so small, it can travel way faster than any other ion. And so a traveling charged particle is all you need to conduct electricity. So that makes hydronium the best electrolyte, the best conducting ion in solution. So the hydronium ion, H3O positive, is able to transfer charge through aqueous solution much, much faster than any other ion can do. That's why acids are the best electrolytes. They're like super electrolytes. Better than any other kind of electrolyte. I'm just going to go ahead and say that. I know that's crazy. I'm going to go ahead and say that. The result is that acid solutions are excellent conductors of electricity. That is also something you are supposed to know about acids. That's why we use them, for example, in car batteries. It's a little bit hazardous, don't you think, to have a giant battery in your car filled with heated up concentrated acid. That's kind of dangerous, but the reason we do that is because they're such great electrolytes, we take the risk. Another property shared by aqueous solutions of acids is that they react with many metals, most of the metals. That's one of the things about acids. They are supposed to react with metals. There are very few metals that will not react with acid. And those are what we call, if you remember, the noble metals. Things like platinum, gold, silver, and even copper is borderline. Those are the noble metals that don't react. All the other metals do, the base metals. Oh yeah, acids react with bases. We'll get to that soon. So the base metals are the metals that react with acid. They're all the metals that are above hydrogen in the activity series, which is, of course, most of the activity series. The reaction is really caused by the hydronium ion present in the solution. So there's the hydronium, and it's reacting with the zinc. What we're seeing down here is what is called a redox reaction, which we are going to try to address at the very end of the course. So I don't expect you to fully understand what's going on there. We'll talk about that later. Notice that the hydrogen gas is released and that the zinc winds up with a positive charge. That means it loses its electrons. Okay, so that's a redox reaction, and we will talk about that later. But the point is that hydronium is what is really reacting with the metal. That's what I want you to get out of that. Notice that the reactants are the hydronium, H3O positive, and the metal, in this case, zinc. This leads us to our first definition of acids. It turns out we need more than one, but this is the most generally accepted one. This is the #1 default standard definition. It's called the Arrhenius definition because he was the chemist that came up with it. The Arrhenius definition of an acid is that acids generate hydronium in solution. So notice the reaction. We talked about this before. HCl plus water. Well, if you put the HCl, which is considered an acid, into water, what does it generate? Generate means make, like form, like your parents are your progenitors because they made you. They generate hydronium when they're in solution. Now, generally, what we're talking about here is aqueous solutions. Technically, it does not need to be an aqueous solution. But if it's not an aqueous solution, this process becomes a lot harder to see. It becomes a little more complicated. So we are going to pretty much stick to aqueous solutions when it comes to acids. Here we see several examples of acids that we encounter in this course. Hydrochloric acid is the one I've already mentioned. That's the easiest one to see. That's the best example. That's what I would call the epitome of an acid. And then acetic acid is a good one too. It's just a little harder to visualize what's going on there because it's this bigger polyatomic ion. But notice that it does have hydrogen. Oh yeah, and there's sulfuric acid. Well, it has hydrogen. Oxalic acid has hydrogen. Nitric acid has hydrogen. Every acid needs to have hydrogen. Generally, that hydrogen is listed first in the formula for the acid. Usually it's H something. And that's because that's the H that generally dissociates. So often that is listed first. We will mostly try to stick with hydrochloric acid because that's the easier one to understand. But we will be dealing with all of these at some point. In fact, you've already seen demos with sulfuric acid. That's the one that reacted with the carbohydrates or was the catalyst for the decomposition of the carbohydrates, the sugar demo. And the nitric acid, that was the one that could get copper to react, okay, and the nitric acid demo with the pennies. And we will be seeing the other ones in future labs coming up soon. Arrhenius also defined a group of chemicals called bases. They were kind of like the opposites of acids in many ways. Not in every way, as we'll see, but in many ways, bases are the opposites of acid. So think about it. If an acid generates hydronium, H3O positive, which is like a water molecule, H2O, with one more hydrogen added and a positive charge, well, what's the opposite of giving water another hydrogen? Wouldn't it be taking away one of the hydrogen? And what's the opposite of a positive charge? A negative charge? So the very, very opposite of a hydronium ion is actually OH negative. So OH negative, you might have imagined, well, we write H2O, we write H3O, so why don't we write this one HO negative? Well, it's a convention from organic chemistry, the reason we write it this way. Okay, so OH negative contains hydrogen and oxygen, so you might want to call it hydrogen oxide, but they shorten that to hydroxide. Hydroxide is another very important ion. I'm going to go ahead and say it's the second most important ion in chemistry. It's a very small polyatomic ion, and it determines a lot of things in chemical reactions. So you've got to recognize hydroxide. Do you remember we saw that before? It was the functional group in a whole class of organic chemicals. It was the functional group in all of the alcohols, like methanol, ethanol, propanol, butanol, pentanol. Okay, all the alcohols contain hydroxide as their functional group. So you're going to see that, well, so do most bases. Most bases contain hydroxide, and some bases just generate it another way. We will see that soon. So the Arrhenius definition of a base is just a chemical that, if you put it in solution, probably aqueous solution, it generates hydroxide. That's a base. One way that a base can generate hydroxide, a very simple way, is by carrying it along with it. If you look at this image, it's showing NaOH floating around in water. Let's assume that this is a liquid and they'd be a little less organized than this, but just for simplicity, I have them all lined up. Well, sodium hydroxide is actually a molecule, but when it's put into water, well, just like we saw before, water tends to pull on things, pull on the sides of a polar molecule, and since water is so tough, it often winds up ripping those apart if they're weaker than water. So water kind of pulls on them, and then it causes them to, what's the D word again? Dissociate. And what you wind up with is a sodium ion and hydroxide. So the dissociation of a base is one way to generate hydroxide. It turns out there's another way that we will see a little later. Now notice there's a sodium ion now floating around. Well, guess what? Just like the chloride ion, that's no big deal. You know that sodium is very, very hazardous. It's a very reactive chemical, but that's when it's an atom. Once it's become an ion, well, again, it could float around for billions of years. Our oceans contain so much sodium ions, so many sodium ions that have just been floating around doing very, very little for a very long time. So the important thing here is the hydroxide that is formed. That will cause many reactions to occur, and we will focus on that a little bit later. So the Arrhenius definition of an acid is a chemical that generates hydronium in solution. The Arrhenius definition of a base is a chemical that generates hydroxide in solution. You should definitely know these definitions, and if you're not sure which definition to use, this is the one to use. These are the default definitions for acids and bases, the ones that we use most of the time, and unless otherwise specified, this is the one I want you to use. So we will continue to learn many more things about acids and bases in the future notes. And we will, of course, get quantitative, just not yet. These were the qualitative notes about acids and bases.